All right, so 3.3 part 2. We're going to be looking at the same rules, okay? So remember that our what we know is sort of a running list of the topics and questions that we should be familiar with. And if any of those topics are not familiar, it's a great indication that we should go back and say, what was that formal definition again? What was this rule? What was that rule? Keep that connection between the rules and the vocabulary and the processes all very interconnected. Okay, so we've taken a look at all these rules, and what we're going to focus on in the second half of today is how do we apply these rules? Okay, so it's one thing to say, oh, I know how to do this particular rule, and it's an entirely different thing to say, but do I know when I need to use that rule? Okay. And so let's take a look at some questions here that maybe help us unpack a little bit more of the concept behind it, as well as that decision-making process. All right, so for example 1, we're not solving anything. All we're doing is making some decisions, all right? So in part A, we've got y equals 3x to the 5th plus 2x over 5. And then we have 8x plus 15 over 2x squared minus, or x squared minus 2x plus 3. And so my question to you is, in this case, which one of those requires the quotient rule and which one of them does not? So looking at example A, which one?
The second one.
Yeah. Good. Okay, so let's write this out here in blue, that this requires quotient rule. All right, this one requires the quotient rule. Now, how then could we avoid quotient rule for the first one?
You can remove 1/5 as a constant.
Okay, so I think there are perhaps a few ways to do this. We could bring a 1/5 all the way to the front. That would be okay. And then we could use a constant multiple, okay? The other way that I think might be also valid is we could take this and split it into 2 fractions. And then we have one constant multiple plus another constant multiple. Okay, so any of these ways of rewriting help us avoid the quotient rule. Okay, now to be clear, have we taken any derivatives right here? No, we have not, right? All we've done is that rewrite stage or the simplification stage. That's it, okay? So to avoid the quotient rule, we can rewrite this in a way so that we only need to use power rule. We don't need to use the other rules, okay? So let's ask ourselves the same question for part B. Okay, so we've got 5x minus 4 in parentheses squared, and then separately, we have a different function, y equals sine x plus 2 in parentheses times the quantity 3x minus 1. And so my question to you is, which one of those do we need to use product rule for? And which one of those can we avoid using product rule?
I'd say it's probably the second one again.
I would agree that in this case, we're going to say that it's probably more efficient with product rule. I will say that we probably can also solve this one without product rule, but if we wanted to find a derivative, I think that one is more efficient with the product rule, okay? And if we kind of do something similar over here then, to avoid product rule, how could we rewrite or simplify this particular statement? Yeah, exactly. We could just multiply it out and we would get 25x squared minus 40x plus 16. Exactly. And then we could just use the power rule. Okay. So here we can simplify first. I think in this case that might be more efficient. Whereas in the one with the blue, I think it is more efficient to use product rule. Okay. Now that is definitely a layer that a lot of those, oh, type your function in here and it'll just tell you how to get the derivative. A lot of those websites don't take that into account, like that decision making of what might be more efficient if we're all doing that by hand. So I do want to make that really clear that a lot of times I'm looking for the most efficient method, and that we want to make sure that we're able to make those decisions, that we trust our own computations. All right, so one thing I want us to think about is the decision making. Another thing I want us to think about is this flavor of question, okay? So thinking about this kind of question, what we're really focusing on here is what rules we want to use, okay? So this kind of question focus on rules and less on did I multiply everything outright, okay? So in some ways, for those of us who are like, you know, I always make a sign mistake somewhere. It's really like sometimes I combine an x squared and an x by accident. Like I know those aren't like terms, but when I'm moving fast, it just sort of is really hard to keep track of that. These kinds of questions are a great way for you to say, hey, I actually know what rules we're supposed to use and I can plug things in. Okay, so it's like almost taking out a lot of that algebra piece and focusing on the actual rule. Do I need product rule, quotient rule, power rule? What do I need? Okay. So let's unpack this particular question. All right. So it says, suppose that we have f of 5 equals 1. So let me just pause there for a moment. Can someone interpret for me what f of 5 equals 1 means?
Some function with x equals 5 equals 1.
Exactly. So we have some function, we're calling it f. When the x value is 5, the y value is 1, right? And that's all that that is saying. Now, what is this in the green saying? F prime of 5 equals 6. If we interpret that, how can we rephrase that? Great, great. So I love all the different ways that we're saying this in the chat right now. So the derivative of a function f at x equals 5 is 6. That's sort of like the most basic way we could say this. But what I really appreciate about what Abby's saying is that we're looking at a derivative at a specific point, right? So specifically at x equals 5. And just like Luca's saying, he's interpreting it to a different level, which is, yeah, we're looking for the derivative, but what does that mean? That means that the function f has a slope of 6 at x equals 5. Okay. So we have that information. Now, let me ask you a question. Do we know what, let's say, f of 7 is, given this particular question? Like, with the information they gave you, could we find f of 7? Yeah, and I think that in particular is really scary for some people. You're like, this is literally information about one point on the entire curve. They don't tell you about any other point on there. However, if you look at all the questions that we're going to be looking at, they all deal with when x equals 5. So it's okay that we don't have information about the other points, because turns out we don't really care about those other points in this particular question. Okay. Now, similarly, I bet you could tell me that g of 5 equals -3 means that when we have the g function at x equals 5, the y value is -3. Okay. And then last but not least, in our Easter eggs assortment of colors here, we have g prime of 5 equals 2. And that tells us that the slope at x equals 5 of the g function is 2. Okay. So now that we've looked at that, let's take a look at question A. So question A says fg derivative of 5. And so I'm wondering if you can tell me what rule they're hoping that we use in order to find the derivative. All right, I see one guess in the chat. What are our other thoughts? Find the derivative of, let's see. If I have fg, maybe another way to say that is f times g. Okay. So we're looking for the derivative of f times g. And since we have two functions that we're multiplying together, that cues us to use the product rule. Okay, so the times here is saying, hey, we want you to use the product rule. Okay. All right. So let's write down the product rule. If I have f times g, all right, this is really saying f of 5 times g of 5. And what we're going to do when we take our derivative is we're going to take the derivative, set up like our u and our v, our du and our dv. And when we plug that into the product rule, we're going to get f of 5 times g prime of 5 plus g of 5 times f prime of 5. Okay. So we have that product rule. Now, you'll notice that I write everything with the f and the g. Like I didn't plug in any of these numbers yet. a general rule of thumb is you want to take the derivative first, and then at the end, you plug in the numbers. Okay. Now that we've got our product rule, let's go ahead and substitute in the numbers that were given from our question. So everywhere that I see f of 5, I can replace that with 1. What can I replace g prime of 5 with? Yeah, I can replace it with 2, right? G prime of 5. The question told us it was 2. All right, what can I replace g of 5 with? Good. G of 5 corresponds to that light blue one, which is -3. And then f prime of 5, I can replace with 6. And so I'll end up with 1 times 2 plus -3 times 6. And so that will give me 2 minus 18, which gives me -16. Okay. So a different flavor of problem, not a lot of like, simplify this, don't forget to FOIL that, but it's very much about, can you tell us what rule you need to use? Can you apply the rule and then crank out some numbers? Okay. So are there any questions here about how we found an answer for number A, letter A? Knowing that, we're not going to do the computation. Oh, okay. So just to reiterate, we identify we're multiplying f and g, and then we plug it into the product rule formula. That is exactly what we're doing. Yes, that is exactly what we're doing. Okay. So knowing that, if we were to take what was just said in the chat and apply that to B, what rule should we be using for part B here? Good. We're going to be using product rule again here. Okay. Now, yeah, exactly. The same. Yup. Okay, now here's the thing. Do you notice that here I have f times g and here I have g times f? Does order matter when we multiply? Exactly. That order doesn't matter. What do you think the answer of part B is going to be? You got it. You got it. So let's actually write that in here, that order does not matter when multiplying. So our answer will be -16. All right, so A and B have the same answer because we're still taking two functions and multiplying them. However, the order doesn't matter when we multiply, so we're gonna get the same answer, okay? Now, let's take a look at C and D, okay? So same yellow, green, blue, and red information above. And if we were to think about a rule we might need for letter C, what rule would you tell me to use?
quotient rule.
Yeah. We're gonna need that quotient rule here. Okay. And in particular, we might note that f equals the numerator and g equals the denominator. Okay. And so what we're going to do is we're going to go ahead and set this up here. Okay. So as far as a setup goes, if I were to find the derivative here, then I would go ahead and start with g of 5 times f prime of 5 minus f of 5 times g prime of 5 all over g of 5, and then I'm going to square it. Johanna, I kind of answered that question earlier. It depends on the question. If we see a one that we can simplify easily, I would expect that we simplify it easily. So I don't want to say we always use that rule, but if we cannot simplify it, then we would use the quotient rule. Okay, so I expect that to be an active part of how we approach the question, is not just autopilot, like, oh, every time I see a fraction, I'm going to use quotient rule. I want to see that decision making, like, is it better in this case to use quotient rule, or is it better to simplify first? Okay. Okay. All right, so once we have all this, we can plug in the numbers that we have from above, and I'll leave that to you on your own time to plug in the numbers. But once you plug in the numbers, you should end up with negative 20 over 9. Okay, so I'll leave that for you to double check, but you should end up with negative 20 over 9. Now, knowing that when we did product rule, the order didn't matter and we got the same answer, what are our thoughts about D? Do we think we're also going to get negative 20 over 9? Or do we think we'll get another answer, a different answer?
Another answer.
Yeah, we're going to get another answer, okay? And so let's make that really explicit for ourselves here, that A, we're going to use quotient rule. Okay, so that's something we're going to write down. We are going to use quotient rule here. And order does matter when dividing. So our answer will not necessarily be negative 20 over 9. Okay. In fact, in this case, the order or the answer will not be negative 20 over 9. Okay, so I see a question in the chat. Order matters because of the negative sign. Well, let's just think about in general when we're dividing. If I divide 1 by 5, is that the same as when I divide 5 by 1? Exactly. So anytime we're dividing, right, the order is going to matter. Exactly. And so in this case, we can see like 5 divided by 1 is a whole number. 1 divided by 5 is not a whole number. Those are different. And so that's sort of why when we use the quotient rule, the order matters when we divide, and the order matters in terms of where we plug in things into the quotient rule. And so on multiple levels, the order matters. Okay. And so when we plug things into the quotient rule for this one, we're going to end up with f of 5 times g prime of 5 minus g of 5 times f prime of 5 all over, what's the denominator going to be in this particular fraction?
F of 5.
F of 5, and we
Squared.
are going to square it. Perfect. Okay, so again, I'll leave those computations up to you, but plug in a few numbers and you should get 20. Okay. So a few main takeaways here that we can tell often by the way the question is set up what rule we are wanting to use. Okay. Second, it's okay if we don't have the actual functions. Sometimes we just have specific points that we're interested in. And with those points, we should always plug in the points at the very end rather than at the beginning. Okay. And finally, when we're looking at product rule, the order does not matter. However, when we look at quotient rule, we need to be very thoughtful about that order and making sure we plug things in the right place. Okay. All right, let's take a look at example 3 now. It's going to be one more new flavor in terms of how these questions can be asked. Okay. And instead of having all points, in example 3, we're going to have one point and then sort of a general function, right? So we're blending some of our strategies here. And so let's take a look at this. If h of 2 equals 4 and h prime of 2 equals -3, find the derivative of h of x divided by x at a specific point 2. And so before we begin, I'm wondering if based on this, you can tell me what rule or rules we should be using to find that derivative.
I'm gonna guess it's quotient rule.
We definitely want to use quotient rule here. Okay, we definitely want to use quotient rule. We want to use quotient rule because we don't have a lot of information. All right, so if we had more information, maybe we could simplify it, but we don't know what h and what that function looks like. Okay, and since we don't know exactly, we kind of have to play it safe and say, let's use the quotient rule because it might simplify, but we don't actually know. Okay. And since we're going to use the quotient rule, let's go ahead and follow that same process we've been doing. We're going to set things up, and then we're going to plug things into the formula. And so if we wanted to think about our u and our v in this case, what would our u and v be for this particular function? Good. U would be h of x, love it, and v would just be x. And so we can kind of see here that our numerator is our u and our denominator is our v. Okay. All right, let's go ahead and find du and dv. And these shouldn't take too long for us to find. How can we express the derivative of h of x? All right, give me one step before that. All right, so Luca, we're going to use that number in a little bit, but for right now, let's write it as h prime of x. Okay, so we'll stick to our notation, but we are going to substitute numbers all at the very end. Okay. Now, if we look at v, though, v is x, and our dv then just becomes 1. Right? Our derivative of x is just 1. So we're using different kinds of rules and notations here, but all in the same problem, and that can get confusing sometimes. Okay. But once we've set these up, now let's sub into our formula. And since we're using our quotient rule, we'll say y prime equals v du minus u dv over v squared. And we're going to plug in all of the information we set up. So this is going to be x times h prime of x minus h of x times 1 all over x in parentheses squared. Okay, so we've just subbed into the formula. And now in our last step, we're going to plug in our numbers and simplify. Okay, so what number can we plug in for x? Yeah, we're going to go ahead and plug in x equals 2. Now, how did we know that? Well, way back in the problem, it said x equals 2, right? So we're going to have 2 times h prime of 2 minus h of 2 times 1 over 2 squared. And now we can use the earlier suggestion that everywhere we see an h prime of 2, we can plug in -3. So 2 times -3 minus everywhere we see h of 2, we can plug in 4 times 1 over 4. We're going to be really careful about our mental math here. We're going to get -6 minus 4, which is going to give us -10 over 4. This is a fairly straightforward simplification, so we'll leave it as 5, -5 over 2. Okay. So different flavor of question, right? Half of it is very similar to what we did in example 2, where we have this function. We don't really know a lot about it, but we can find the derivative by just saying h prime, right? So h and our h prime. And then the other half of it was going back to what we know about power rule, that we have a defined function as x. And then how do we find that derivative? Well, it just becomes 1, okay? Before we move on to example 4, are there any questions about example 3? All right, let's go on and move on to example 4 then. So example 4, given f and g are functions whose graphs are shown below. And we're defining two functions here. We're defining u of x as f times g, and we're defining v of x as f divided by g, okay? And we've got this picture. And so let's see what we are being asked to do. So in question A, it says u prime of 1. All right, now u is f times g. And so what rule are we being asked to use in part A? We are being asked to use that product rule, absolutely, okay? Because we're told that u of x is f times g. And so we can come here and say, yes, I know I'm going to use the product rule and note that for ourselves. And while we're annotating, what could we say the rule is that we're going to need for part B? Exactly, because we've got f divided by g. All right, so being able to identify that rule right off the bat is super important. Okay, so now let's use our product rule. Let's set up our product rule. So typically when we have a product rule, we have our two functions. So we have f of x, and then we have our g of x. What would we say the derivative of f of x is? How would we write that? Exactly, f prime would be the derivative. And what would we say is the derivative for g of x then? Exactly. Okay. So sometimes we're like, well, but I don't know what the derivative is. Like, I don't have an equation and that feels so uncomfortable. But here we're just setting up like our functions and their derivatives because we have numbers that we're going to be able to find from our graph. Okay. So if we sub into the formula, we'll get u prime of x is f of x, g prime of x, plus g of x, f prime of x. Okay, so that's our general formula. Now, because we've been so very patient, now we plug in the numbers. Okay. Now, in particular, what number am I going to replace x with? Great. We're going to replace every x that we see with a 1. So because this is a 1, oops, because this is a 1, everywhere I see an x, I'm going to be able to put a 1. Okay. So u prime of 1 equals f of 1, g prime of 1, plus g of 1, f prime of 1. Right? So far, we've only used what we know. We haven't even used the graph at all yet. But now, in order to finish the problem, we're just going to grab all the values we said we wanted. We're going to grab them from the graph right here. Okay. Now, I bet folks can tell me what we have for f of 1. Let's just draw this in a little darker. But what can we say f of 1 is? Yeah, f of 1. So f is the pink curve. So if I go to f of 1 and draw a dot, that has a y value of 2 according to the diagram. Right, so this is 1, this is 2. And so everywhere I see f of 1, I can go ahead and plug in a 2. How in the world do I find g prime of 1? Ooh, okay. So g prime of 1, if we think about what that means, is the same as asking for the slope of g of x at x equals 1. Okay. So now the order in which we look for this is very important. All right. And so Sophia, we don't want to find the y value and then find the derivative. We want to go to the picture and we want to look at what the slope is. All right. This is why we wait to plug in our numbers until the very, very end, because otherwise everything's going to be 0. And unfortunately, life is not that easy. Okay. So we're going to go to the g function. And I'm going to zoom in on this g function, which is the blue one. And if I know that at x equals 1, what is the slope of g of x? Oh, you're super close. I appreciate where you're going. Yeah. It looks like so close, not 1, because the direction in which that line is going is super important, right? That slope is -1. And we can find that just by saying like our rise over our run, right? So that's just a throwback to middle school where we're counting rise over run from a graph. So everywhere we see, let me line these up a little bit better. Everywhere we see the g prime of 1, we can say that's -1 because we literally counted the slope from the graph. Okay. All right. Can you tell me what g of 1 is? All right. That's really asking what's the y value of that blue point? It is indeed 1. I don't know why my parentheses look so weird there. Last but not least, what is f prime of 1? We got to go back to the graph. What are we looking for on the graph?
Slope at 1.
Yeah, exactly. We're looking for the slope of the pink function at 1. And so when we count that rise over run, whoops, we'll get a slope of 2. Okay. Good. Now I saw something in the chat. We only know that g prime is -1 because of the graph. That is absolutely correct. So we know because we went to the graph and we said at x equals 1, what's the slope? And it turns out it was a -1. Okay. All right, so we've got all those numbers. 2 times -1 is -2 plus 2. And it turns out that the slope when we take the product is just going to be 0. I know that is like sometimes the worst in all of these math problems. You get to the end and it's 0, or you get to the end and it's 1. All right. But part of this is so that it's sort of crafted in a way that it's okay that our numbers aren't going to be outrageous. All right. All right. So to find the slope, we go from the point to the peak or high or low of the function line. It doesn't have to be. You literally can take any point on this line, any 2 points, and find your rise over run. So like I could have picked this point and this point and found that rise over run. Or I could have picked this point and this point and find rise over run. So it doesn't have to be any one way. You just have to find the slope at that point. Okay. But let's practice that again, okay? Because this time we're looking for, in part B, v prime of 5. And earlier we said v of x is f of x over g of x, which is why we said, ooh, we're gonna need that quotient rule, okay? So let's set this up in terms of our quotient rule. We're gonna have f of x, g of x, right? Because f is the one on the top, g is the one on the bottom, and then our derivatives, f prime and g prime, all right? We're going to be really, really patient and say no plugging in numbers until we get to the very end, because otherwise we might mistake it and get a bunch of zeros. All right, if we want to sub everything into the formula, we better use the quotient rule. All right, we have to use the quotient rule here. And so our derivative, we would get v prime of x equals, all right, the numerator is f of x, the bottom is g of x. So when we plug things into our formula, we're going to have g of x times f prime of x minus f of x, g prime of x, all over g of x squared. All right, so we're just plugging that into the quotient rule. And now, what number are we going to replace all of the x's with? Okay, how come it's not 1? Let's just unpack that for a second. Why aren't we looking at 1 anymore? The problem is asking for a different value, right? So we need to pause and we need to say, what x value am I looking for? And we need to make sure we use that right coordinate, okay? And so if we now think about what we have, we're going to have v prime of 5 equals g of 5 times f prime of 5 minus f of 5 times g prime of 5 all over g of 5 squared. Okay. So I'll give you a moment to look at the graph and find the corresponding values and start to plug those into your equation. I'll give you a little bit of a head start and then I'll go ahead and plug those numbers in as well. All right, but we're looking from the graph. How do we find g of 5? How do we find g prime? How do we find f of 5? How do we find f prime of 5? And making sure that we plug those all into the correct location. All right, so I'm going to start to fill in some numbers here. You let me know if you agree or you disagree. Okay, so from the graph, whoops, sorry. From the graph, I said that the y value of g at 5 is 2. So if I were to highlight that point on the graph, 1, 2, 3, 4, 5, that might be like right here. And if I were to find f of 5, that would be like right here. Okay. Ah, good. Okay. So I did intentionally drop a sign here. I want to make sure that we're really thoughtful about slope and whether it's positive or negative. But if we look at the slope of f, that sure looks like it is falling when we read from left to right. And so instead of a 1/3, we would want that to be a negative 1/3. Okay. Now, I did not intentionally make any other mistakes here. So if there's anything else, let's just double check this right now. Do we all agree with the rest of the numbers that I have here? Yes. Okay. And so as far as simplifying this goes, we're going to get negative 2/3 minus, let's go with 6/3 all over 4. So this gives us 1/4 times -8/3, which gives us -2/3 as our answer. Can you explain why it is 1/3? It's supposed to be -1/3. Oh, okay, let's go see. So if I were to count, and this goes back to Catherine's excellent question earlier, I just need to find 2 points that are sort of nice points and count the rise over run. So I might choose this one and this one. So I go down 1 and then over 1, 2, 3. So 1/3, because we're looking rise over run, or -1/3 in this case. Okay, cool. All right. So how we doing with the graph version of this question? Right, lots of different rules here, using a lot of those over and over again. Ah, okay, good, good. Well, we didn't have to do those questions on quiz 4, so hopefully it'll make a little bit more sense now. Yes, it is similar. You really have to know not only what numbers to use, but where you get those numbers from, okay? So as you're working with each other on these, really challenge yourself to think, where are these numbers coming from and how do we know, all right? All right, so, let's go ahead and take a very short break. I feel really bad asking you to sit for so very long. So let's just take a very quick stretch break. Let's be back at 9:06, all right? And then we'll finish up what we can finish up today, all right? So go take a quick body break, be back in 5 minutes, and we will finish up the rest of our lesson. All right. So let's take a look at the next topic, which is higher order derivatives, okay? Higher order derivatives. So this will probably be where we finish off today. I just want to make sure that we understand what a higher order derivative is. But a question I have for you is, if the derivative tells us about the steepness of an equation, and we might say steepness is sort of like our way of describing slope, okay? But if the derivative tells us about the slope of an equation, what are your thoughts on what a second derivative tells us? I'll give you a moment to kind of think about that, but what do we think that second derivative tells us? All right, any guesses? All right, so I see something about more slope. Okay, can we be more specific about that? Slope of what? Right, so maybe the second derivative tells us about the slope of the first derivative. And it turns out that that is indeed correct. It tells us about the slope, but it tells us about the slope of the first derivative, okay? And one word that we're going to be looking at in chapter 4, and I'll just put that out there in case anybody has seen this term before. It also, the second derivative tells us about something called concavity of a function. Okay. And Diego, that's a great question. How does the concave work? And we're going to talk about that in chapter 4. Okay, so let's just kind of put this back in our brains, that word for chapter 4. All right. But based on what we wrote for the second derivative, I'm wondering if we can tell what the third derivative might give us information about.
The slope of the second derivative.
Exactly, yeah, that slope of the second derivative. And we don't necessarily have a fancy word to put here for right now. So we'll just say it's the slope of the third derivative, okay? But anytime we're looking at a derivative, yes, it tells us about slope, but more specific than saying more slope, we want to think about what is it the slope of, okay? So a second derivative will be the slope of the first derivative. And a third derivative will tell us the slope of the second derivative, okay? And so let's see how that question might be asked, all right? We'll spend a lot more time later on about like what those things look like, but let's see what the procedure might be like right now. And so in example 5, we're given y equals 3x squared plus 8 square root of x minus 10. And in part A, we're asked to find y prime. And so before we find y prime, do we think we should rewrite this one, or are we okay to move on and take derivatives? What are our thoughts?
It's a good idea to put the x to the 1/2, right?
Yeah, I would say let's rewrite this as, whoops, 3x squared plus 8x to the 1/2 minus 10, right? Let's do that square root, rewrite it so we can see the power, because the power rule is great, but only if you know what the power is, right? And so now let's find our y prime. And we'll get, what does 3x squared become when we take that derivative?
6x.
Yeah, 6x, good. Plus, we're going to get 4x to the negative 1/2. Where did that 4 come from? Good, the 8 times the 1/2, perfect, perfect, okay. And then what happens to the 0? I mean, the 10, totally just blew my own surprise. Not 10, right? The derivative of 10, that goes to 0. And if we were to rewrite this as a final answer for y prime, we might write it as 6x plus 4 over root x. All right. I want to find y, but with 2 primes. So this was our first derivative. Y with 2 primes is asking us for the second derivative. Okay. All we do, we take our first derivative and we repeat the process. whatever rules we need, we're going to use those rules. What rule are we going to use to find the derivative of 6x? Yeah, we're going to use that power rule. And so the derivative of 6x is going to give us what? 6, perfect. So the 6x, I take the derivative one more time, I get 6. And if I want to find the second or another derivative, is it easier to use 4 over root x or 4x to the negative 1/2? Which one is easier to find a derivative? The one with the negative 1/2, exactly. Okay, so now we're going to use our power rule here. So I'm going to get minus 2x to the negative 3/2. Where did that negative 2 become? Because I thought it was a positive 4 before. How are we getting a negative 2 in the front?
Because we're multiplying 4 by minus 1/2.
Exactly. This positive 4 times negative 1/2 is going to give you negative 2. Okay. And when I lose a power, negative 1/2 minus 1, that gives me negative 3/2. Okay. Now, if I were to write a quarter final answer for the second derivative, I might write 6 minus 2 over. Now, I know there's a root, but what number goes out here? Yeah, that's going to be a 2. And it's one of those invisible 2s where it's understood to be there, but we don't usually write it because that's our square root. Okay. And then what number is the power underneath that radical? That one is going to be 3. Okay. So the little 2 you don't have to write, but the big 3 you do have to write. Okay. All right. Why triple prime? What am I asking you to find in part C?
The slope of the second derivative.
Yeah, that slope of the second derivative, and that is equivalent to saying find that third derivative. Right? And so, like before, do we think this way is easier to find a derivative or our final answer? And I think we might agree that the first one, where we can actively see that power, is the one we want to use. Okay. And so y triple prime equals 0 plus 3x to the negative 5/2. Okay. Where did that 0 come from? The
Constant
derivative
number.
of that constant, exactly. Now, why did I have a negative 2 here and all of a sudden I got a positive 3? How did that happen? Good. I had a negative 2 and I multiplied it by negative 3/2. And so negative times a negative is a positive. Good. And if we were to rewrite this as a final answer, we might write 3 over. If we were to only write the number we need, where would that number go? And what is that number?
X to the 5th.
Yeah, we're going to have an x to the 5th. Okay. The 2 is invisible. It is there, but you don't have to write it. But that x to the 5th, that 5 does need to be there. All right. So how are we feeling with those derivatives there? higher order derivative, you just keep taking the derivative, okay? But you do have to use whatever rule is needed, okay? So if there is a derivative of a quotient, you're going to need quotient rule. If you have products, you're going to need product rule. So it's whatever rules you see there, you kind of have to recheck that at every step, okay? Yes, and so we'll talk more in chapter 4, like what these things even are about. And actually, we'll talk a little bit about it tomorrow as well, okay? But this seems like a good place to stop for today. I would encourage you to look over quiz 5, okay? So start looking at quiz number 5. I did update this quiz this morning, so please make sure you have the latest version, all right? So if you printed out something last night, that is no longer the version. However, if you go and look at the document right now, it should be updated, okay? And I would encourage you to work through whatever questions correspond to what we covered in lecture today as soon as possible. All right. So some of us, I think, are really good about working a little bit every day on this. Some of us are waiting until 11 o'clock on Wednesday night and then wondering why we're turning in sort of rushed work. Okay, so please take the time right now, especially in an accelerated summer course, to do a little bit every day, whatever you can do. That way you have time to ask me questions, okay? If you ask me a question on Discord at 11 p.m., I will not be awake and I will not answer you, okay, because I'm not awake. But if you ask me questions sort of throughout the day, it's easier for me to support you in your learning. Whereas if you wait until super late at night, I can't always support you on that, okay? So as far as that goes, you do not need to complete quiz 4, okay? So I did copy and paste the questions I thought would be most important in the updated version of quiz 5. If there are questions from quiz 4 that were not copied over to quiz 5, you can use those as extra practice and studying, okay? So that's how we will leave that. You do not need to finish up the rest of the questions. And there is a trig activity on Desmos due today. For the last question, I would encourage you to look those up on the interweb, okay? So think of that as a preview for what we're going to learn on Wednesday. Also, how can we develop our Google skills? Okay. All right. Bye, folks. Have a great rest of your day. I think I have meetings with some of you later today, so I'll see you then. Otherwise, I'll see you tomorrow morning. Bye, folks.